Welcome back. Part 2 of the rate of change video. Last time we did the derivative stuff. We did the instantaneous rate of change stuff. We did it for this example. We did it with 3, then we did it with 6. Pretty easy. Not too bad, right? A little bit of work, not too bad though. So we finished the example 4.5. Now we're going to flip it over and do some more, right? All math classes. More examples, more work. Okay, here's a cool picture that represents the last one. Remember, it had a slope of -8, so -8, and then the units would be hundreds of dollars per day, right? You're losing a lot of money. That's right. Sucks for them. Next one. Find the equation of the line tangent to this graph at x equals 1. So equations of tangent lines. Those are pretty common Calculus 1 type questions. They're not hard. The worst thing about it right now is going to be finding what the slope of that darn tangent line is, right? Finding the derivative, finding that instantaneous rate of change, because we're going to need to use that limit process. Once we get the shortcut rules, that's coming next time, so it's gonna make our life a lot better. But once we have the shortcut rules, this process is going to get a lot faster. But if you want to get the equation of a tangent line, here's how we can go about doing that right now. Remember, there's two really equations of a line. Actually, there's three. There's standard form, but we never really use standard form. There's slope-intercept form, which is y equals mx plus b, and you would use slope-intercept form if you happen to know the slope of a line and you knew the y-intercept of a line. It's very rare that we know the y-intercept. Typically, we know some other random point, right? And we could use that random point, like here it says at 1. So I know that point on the graph is the coordinate point 1, 1. This graph doesn't even have a y-intercept. Well, I guess the tangent line would, right? So I guess you could try to figure out the slope and then work your way backwards and try to guesstimate or actually find out where that tangent line would have the y-intercept. But it's just so much work. Like, why would you do that? There's a much easier way, and that's called point-slope version of a line. Y minus y1 equals m, x minus x1. That's your point-slope version of the equation of a line. Slope-intercept is fine, but we don't typically know the intercept. Standard form's terrible. Don't use standard form. Point-slope is really what we're going to use, right? If you know a point, and if you know the slope, and we're going to figure out the slope from that limit, from that derivative process. If you know a point and you know a slope, point slope is the form for you. So that's the one we're going to do, right? So point slope probably is going to be better than slope intercept. If you happen to know that your point has an x value of 0 and it's the y-intercept for the tangent line, great, wonderful. You can go straight to y equals mx plus b. Generally, though, you know some other random points. You plug in the x coordinate here, you plug in the y coordinate here, you use that derivative process, that limit process to find the slope. You plug that in here, right? So slope, intercept, kind of throw that one out the door. Point slope, that's what we want. So let's go for it. Let's finish this one. I'm going to plug in what I know, right? I know this point, the y-coordinate was 1, and I know the x-coordinate was 1. So all that's left, right, that's going to be the answer. All that's left is for us to find the slope of this graph at that specific point, also known as the slope of the tangent line at that specific point, also known as the instantaneous rate of change at that specific point, also known as the derivative at that point, right? All those different words that mean the same thing. Let's go through and do it. We need the limit as h is approaching 0. I'm going to need 1 over x plus h minus 1 over x over h, right? It's your f of x plus h minus your f of x over h as h goes to 0. This one's going to get tiny, right? So if you write big, you may want to get a separate sheet of paper. If you have printed out the notes, you may want to write small like I'm going to do. I'm going to go for it, though. I'm going to try to fit it all in there. I think I probably will be able to. All right, here we go. Some algebra skills time. The denominator I'm going to leave as h. I'm going to do a little trick. I'm going to combine those fractions in the numerator. It's a little trick called fast adding. Basically, all you have to do, cross multiply to get the top. So I've got x minus x plus h. Cross multiply to get the top. And then you multiply across to get the bottom. Yep. That trick is going to always work. It's a really nice way how you can add or subtract two fractions very, very, very quickly without having to worry about the least common multiple and then fiddling with the left side, fiddling with the right side, getting that common denominator, and then combining them. No, the fast adding trick is much faster, hence the name, and it's also, I think, much easier. So again, you just cross multiply to get the top, whatever this operator is, make sure it stays the same. Watch out for your parentheses. So cross multiply to get the top, and then you just multiply it straight across to get the bottom. That's great. Now here I'm going to put this over 1 because I'm about to do another trick. This next one I call the sandwich trick. And it's going to compress this 4-layer fraction down to just a regular fraction with a top and a bottom. Actually, before we do that, let's go ahead and let's deal with this stuff in the numerator, right? Here that's x minus h. So those x's are going to cancel, right? So these x's cancel, and then you have a negative h. But you still have this compound fraction where you have 4 layers. You have the very top. Remember that very top, I've simplified it. Here, I'm going to cross it off. I distributed that negative. The x is canceled. So the very top of the top, that's just negative h. Then you have the bottom of the top. That's the top of the bottom. That's the bottom of the bottom, right? A whole lot of words going on, but it's a 4-layer fraction. We don't want a 4-layer fraction. That's a fraction inside a fraction. Overall, we want 1 fraction. So we want 1 numerator, 1 denominator. So let's get it. Let's get it. It's from the sandwich trick. Again, you could take this, you could multiply by the reciprocal. That's what the sandwich trick is going to do. It's just going to do it much faster without having to write out the work. Anyways, these middle 2 layers of your sandwich, right? Think about the top, and then you have the 2 layers in the middle, then you have the bottom. The middle 2 layers of that sandwich, they're going to multiply together, and they go to the bottom. And then the outer 2 layers, they're going to multiply and they go to the top. That is going to accomplish the same thing as you would have gotten if you would have multiplied by the reciprocal, which we kind of have been taught. That's how you divide by a fraction. Don't do it, right? You just multiply by the reciprocal. Well, you can do it, right? Sandwich trick, it's going to accomplish that same thing. Middle 2 layers, multiply it, they go to the bottom. Outside 2, multiply it, they go to the top. It's a little bit faster, right? So you have the fast adding trick. That's how you can add or subtract 2 fractions together very quickly, very easily. Then you have the sandwich trick, smushes it down. Now let's go for it. I've got an h that's going to reduce. This h is going to 0, so now I have negative 1 over x, and then x plus h. So quite a lot of algebra. Hopefully you appreciate the little skills that came up. They're pretty useful. And now we can evaluate the limit. Right now I can actually plug in the h is 0, so that piece is going to go away. So I'm going to have negative 1 over x times x. So this derivative function is going to be negative 1 over x times x. That's the same thing as x squared. Remember, next time we're going to get the shortcut rule. The shortcut rule is going to enable us to go straight from the original function to this derivative in like 5 seconds. It's going to be really fast, really easy, but we're not there yet. The limit process will always work, but no, you're not going to need to do it once we learn the shortcuts, right? So hopefully that makes you appreciate how nice those shortcuts are. Next thing, we need to plug in, right? This point is at the x value of 1, so I need to plug in 1 into this function, into the derivative, not the original. And then here I'm going to end up getting negative 1 is the result. So the slope of this tangent line, right, that intersects the graph at 1, 1, the slope of that tangent line is negative 1. So now I'm going to take this, plug it back in, and you're done. You can get it into slope-intercept if you want. You just distribute, and then you add that 1 over. I think here, you'd have a negative x plus 1. So I think you would have, just negative x plus 2. So if you wanted to get it into slope-intercept, you could. It's just 2 extra steps. Distribute the slope, and then move over that extra number. That was the y1 coordinate. But that's just extra work. Unless it specifically asks for your answer in slope-intercept form, you don't need to do it. The point slope is perfectly good. Again, how we got that? In order to get the slope, you have to plug in your x value into the derivative. So you do all this limit work, you get your derivative function. Then you plug in your x value into that derivative function. That gives you the slope of the graph at that specific point. And then in order to get the y1 coordinate, you would plug in your x into your original function. The original is what you plug in to get the y coordinate. The derivative is what you would plug in to get the slope. Okay, next one. Same instructions, find the equation of the tangent line. So I'm going to go ahead and set it up. We got y minus y1 equals mx minus x1. Wonderful. And it says at the point where x equals 3. So there we go. I got one thing already done. I'm going to put a box because that's where my answer is going to magically be. First thing, let's go get the y coordinate because that's easy, right? You just plug in to the original function. That's how you get your y coordinate. So here we go. Plug in 3 to that original function. 3 plus 1 is 4. Square root of 4 is 2. So there we go. That point is 3, 2. Okay. That, by the way, this looks like a typo. X plus 1, x plus 3. That looks like a typo. That should be x plus 1. I was looking at that. I was like, why would it be 3? Okay, that was weird. X plus 1. I don't know why that's mislabeled on the diagram in the picture. That's okay. We've got the correct function here. All right, so we've got x plus 1, square root it. I know if I take the x value, plug it in, 3 plus 1 is 4, square root of 4 is 2. So at this point, 3, 2. All right, let us go for it. Next, let's do the limit stuff. Again, what we want to do is find the derivative function. Once I have the derivative function, I can plug in 3, which will tell me what the slope of that graph is at that point, which is also going to be the slope of the tangent line at that point, which is that value I'm going to plug in right here. So let's go for it. This one's going to be a little bit of heavy algebra. So we got square root of x plus h plus 1 minus the square root of x plus 1 over h, right? Your f of x plus h minus your f of x over h as h goes to 0. Now this one is a little bit stranger because you have these radicals. In the general strategy, if you remember back to the previous limits video, anytime you have a radical, you are probably going to need it to use the conjugate, right? So here we are going to multiply by a very strange looking 1. We are going to use the radical of the numerator, which has the radical terms in it. So we're going to use the conjugate of that numerator, and then we'll be able to get this answer. So here we go. Copy this stuff. Going to multiply by 1, which is the conjugate of the numerator. X plus h plus 1 plus, almost said minus, plus the square root of x plus 1. Anytime you have a square root, and plus or minus some other chunk, even if the square root, even if those radicals are in both of the chunks, your technique is probably going to be use the conjugate, multiply by the conjugate on the top, and then, of course, you have to keep it balanced. Do the same thing in the denominator. Now, the non-conjugates, you're going to leave them factored. So here, the denominator, I'm just going to copy, have that h, and then I have this chunk, x plus h plus 1 plus x plus 1, right? Leaving the denominator, leaving the non-conjugates factored. But then the two things that actually are conjugates, you're going to multiply them out, because when you multiply out conjugates, some stuff's going to cancel. Here we go. First times first, right? When we're going to FOIL first, outside, inside, last. First times first, when you have the square root of stuff times the same square root of stuff, all that's going to be left over is that stuff. So the square root of x plus h plus 1 times the square root of x plus h plus 1. It's just going to be x plus h plus 1. No square roots, right? They canceled. Then you have the outside, so you have plus one of those mega roots, right? You'd have x plus 1 times x plus h plus 1 inside the radical, but you'd have plus 1 of that value, then you'd have minus 1 of that value. So you have this weird square root times the square root with positive, then you have the square root times the square root that's negative. Those two middle terms are going to cancel when you multiply out conjugates. So I'm not going to write them. They're going to cancel. So we have the first, then we had the outside, the inside. Those are going to cancel. So then we just need the last. Make sure you know negative times a positive, that's a negative. Square root of this times the same square root of this is just this. And then let's see. We have x plus h plus 1 minus x minus 1. The x's will cancel. The 1's will cancel, leaving me with just the h. And look at that. Or I guess I'll regroup it. Okay, let's see what we got. We got limit still as h is going to 0. We still have this h in the numerator, but you still have this also h in the denominator. X plus h plus 1 plus x plus 1. All right, so we multiplied by a weird-looking 1 using the conjugate of the radical term, multiplied by it, FOILed out the conjugates, left the non-conjugates factored. Then I distributed in the top. The x is reduced, the 1's reduced, still have the h, and now the h is reduced. How wonderful. And then that's just a 1 on the top. Once you reduce it, then you can go ahead and plug in. That h is going to go to 0. So I have 1 over the square root of x plus 1 plus 0. Don't need to write plus 0. Plus the square root of x plus 1. Am I on the screen? I still am on the screen. How wonderful. So this, you could rewrite it as 1 over, and if you have a square root plus the square root, that's the same thing as 2 of the roots. So here is your derivative function. If your original function is the square root of x plus 1, your derivative would be 1 over 2 square roots of x plus 1. All right, so there's your derivative function. And then the last thing you would need to do, right, that's f prime. Next thing you need to do is plug in my specific x value, which would be 3. 3 plus 1 would be 4. Square root of 4 is 2. 2 times 2 is 4. So it looks like the slope of the graph at that specific point is 1/4, right? That's the slope of the curve at that point. Remember, the curve changes slope. It's not always going to have that same slope, but at this one specific point, that curve has a slope of 1/4, and also that tangent line has that same slope of 1/4. So then we just put the 1/4 up there, and then we're done. Again, you could distribute and you could get it into slope-intercept form, but unless the question specifically asks for it, why, right? Why? Why do you do extra work? Extra work is just an opportunity to make a mistake. Don't do it. Stop with the point-slope form. It's perfectly okay. Unless it specifically asks for y equals mx plus b, if it asks for slope-intercept, then you have to do the extra algebra. But if it doesn't ask, don't do it, right? It's just silly. All right, last page. We're almost done. We're getting there. Here we go, 4.8. All right, need to scroll it down a little bit more. Arlen's Air Service provides airline service, go figure, for private individuals. The cost of flying from Austin to Denver can be modeled by this function, c of x, where x is the number of round trips and c is the cost in hundreds of dollars. So we got the number of round trips, hundreds of dollars. Watch out for your units. Arlen has found that the instantaneous rate of change of c, also known as the derivative, is given by this function. Oh, look, how lovely is this example? We're not going to have to do that f of x plus h minus f of x over h is h is 0. We're not going to have to do that because they've already given us the derivative function. That's very wonderful. Yes, that is the correct derivative. Yes, it would take you only about 2 seconds to do once we get the shortcut rule next time. It would take you about 5 minutes to do. If you had to do it the long way, it would involve a lot of multiplication, a lot of reducing, but it would work. If you had x plus h cubed minus 12x plus h squared plus 36x plus h plus 50, that's all just the top left piece minus the original function over h. It will work, but why do it, right? It already gives you the derivative, so that's nice. Gives you the original, and it gives you the derivative. All right, find the slope of the line tangent to c at x equals 8. So we want to find that instantaneous rate of change to c at 8. All that means, take that derivative, plug in 8, right? The derivative function tells me what the slope is at any given point, so all I need to do is plug in 8. So I have 8 squared minus 24 times 8 plus 36. And it looks like if you do all of that, let's see, I think that should be 36. Check it with your calculator, but I'm pretty sure it's right. And then 36 is the answer. Okay, so let's go ahead and interpret this answer. So there's the slope, right? I guess you don't really need the units if it says just find the slope. The slope is a number, right? So the slope is 36. It's very, very steep tangent line. That's okay. Now let's do the interpretation. The interpretation. The cost of flying on the 8th round trip was increasing. Remember, increasing because it's a positive rate, was increasing at a rate of, that's $3,600, so $3,600 per round trip. So those flights are getting more expensive, right? And specifically on that 8th round trip that you're going to increase, the cost for adding on that next trip looks like it's increasing at a cost of $3,600 per round trip. Okay, so it gave us the derivative, plug into the derivative. How lovely, we're done. Last one, 4.9. The figure below, G represents the number of units a company sells in 1 month, and X represents the day of the month. Determine whether the slope of the tangent lines at A, B, and C are positive, negative, 0, or undefined. Interpret your answers. Oh my gosh, okay. This one's pretty quick. If it only didn't say interpret your answers, this would be really quick. It's still mildly quick, but it's a little bit more annoying. Part A. Let's look at it. If I were to draw a tangent line to point A, it definitely looks like that tangent line would have a positive slope. Right. And really the better notation for this, or the better terminology for this, we would say the function G is increasing when it has a positive slope. But certainly I could see if I were to draw the tangent line, that tangent line would have a positive slope. So let's go for it. Tangent slope at x equals A is positive. I'll say therefore, let's go ahead and get this interpretation done. Therefore, the instantaneous rate of change, that's the same thing as the derivative, is greater than 0. So the units, or the number of units sold, so the number of units sold is increasing on that particular day. Whatever that x value is corresponding to the point A, that would be the specific x values. But on that particular, I can get it, day, kind of. There we go. Sorry, I was getting a little diagonal. Definitely has a positive slope. Positive means increasing. So there we go. Part B. If I were to draw the tangent line that hits the graph at point B, it looks like that tangent line is perfectly horizontal. And then I'm going to ask you the 50-50 question. Hopefully you guys all get it right. Is the slope of a horizontal line 0 or undefined? We know it's not positive. We know what positive slopes look like. We know what negative slopes look like. It's just the zeros and the undefines that people get messed up on. Hopefully you remember, but the slope of a horizontal line is 0. The slope of a vertical line is undefined. So here we go. Tangent slope at x equals b, come on, pencil, is 0. Therefore, the number of units sold is not changing. So you could say not changing, or you could say is neither increasing nor decreasing, right? It's constant, right? You could say the number of units sold is constant, or you could say the number of units sold is not changing, or you could say the number of units sold is neither increasing nor decreasing. All right, that just means it's all staying the same, right, on that particular day. Okay, and then logically, we think, okay, A was positive, B was 0, so I'm guessing C is going to be negative. Let's have a look-sees. Yep, it looks like if you were to draw that tangent line, it looks like that tangent line would have a negative slope. So let's finish this one. Tangent slope at x equals C is negative. Am I on the screen? I think so. Therefore, the instantaneous rate of change is less than 0. Slope of the tangent line, instantaneous rate of change, derivative. Those are all three interchangeable. They mean the same thing. The instantaneous rate of change is negative. So the number of units sold is decreasing. Negative rate means decreasing on that particular day. On that particular day. I don't want to write it again. I'm lazy. Positive slope means increasing. Negative slope means decreasing. 0 slopes means neither increasing nor decreasing, so you could say constant, right? And the derivative is going to tell us whether the specific function is increasing or decreasing or 0 at all of the individual points. This one, we only had to look at it, and it was pretty easy to see positive, 0, negative, but the derivative function is going to enable us to plug in and mathematically prove what the slope is at any point. So yes, a very useful tool, the derivative. That's what the majority of this next month or so is going to be about: differential calculus, these instantaneous rates of change, slope of the tangent line, derivative, and then all the applications we can do with it. Thanks for watching. I'll see you, I guess, probably soon.